Okay, so let's imagine that we have an object launched from ground level, and we launch it upwards at a speed v naught. And the question is, what is the height that it rises to? So what is y max? Okay, so this problem, like the problems we've been exploring in the last few lectures, are all problems that we can solve in one line, but we don't have the techniques to solve them in one line. We're forced at this point to go through time. So we can see that we're forced to go through time because y max, right, there's a kinematic equation that gives us the y value, and that is the initial y, which is 0. So that's 0 times the initial vertical component, which is v naught times t, minus 1/2 times g t squared. And so we see that in order to get this y max, we need to know what t is. In other words, what is the t when the object reaches its maximum height? And so that forces us to go to the next kinematic equation, which says that the y component of the velocity is the initial v naught minus g times t. And so we want the specific time when the object reaches its maximum height, which means that we have to think dynamically. It reaches its maximum height when this quantity is 0. And so that becomes 0. And so what we get is that the t that we care about is equal to v naught over g. And so we can plug this into this expression and get our y max. Right, it's v naught times that t, so let's put it in parentheses, v naught over g minus 1/2 times g times that t squared, which is v naught over g squared, and that reduces to v naught squared over 2g. And again, we'll come back to this type of problem, and we'll see that we'll be able to solve it in one line, unlike here where we needed two equations. Let's do a slightly different version of this problem. So let's say that we launch the object again at a speed v naught, but now at an angle phi, and we ask what is the maximum height, again, y max. Right, so it's the same question. We'll see that the answer requires the same strategy, but with a slight difference. So y max in this case is equal to the vertical component, which is not v naught, but v naught sine of phi times t, minus 1/2 gt squared, which again we see we have the same issue. We're going through time. We need to know the time when the object reaches its maximum height, and that occurs when the vy value, which is not v naught, but v naught sine phi minus gt, is equal to 0. And so in this case, we get a time which is v naught sine of phi over g. And so our y max in this case becomes v naught sine of phi times t, which is v naught sine phi over g, minus 1/2 times g times v naught sine of phi over g squared, which is, well, let's write it here. It's v naught squared sine squared of phi over 2g.